Hi, my name is Alex Nimmo. I'm part of Group A6 for Aerospace 305. Today we're going to do a presentation about LabA3, testing a 2D airfoil that we did about 3 weeks ago. Today I will talk about the introduction, why we did the experiment, the results of the wake profile, and also the procedure and how we did the experiment. So the introduction, the purpose of this lab is to get lift and drag coefficients of a specific airfoil. The airfoil that we used was the S805 airfoil, as seen as this figured right here. It is a 2D airfoil, so it just stretches the span of the wind tunnel. So we want to get lift and drag coefficients there. We also want to get the wake profile of the airfoil. To do that, we use a hot wire anemometer that we used in Lab 2. We use the same calibration factors and the same results that we got from Lab 2 to help us out in this lab to get the wake profile. We also want to try to find out what angle of attack the airfoil stalled at, and that will be discussed in the next slide or so. And also the CL and CD values that we calculated were compared with other data in previous labs and also NREL data that was given in class to make sure we're on the same track and we're not going off the rails. So the overall procedure, we started by measuring the atmospheric temperature and pressure, the atmospheric temperature and pressure in the wind tunnel in the lab, and we used that to calibrate the wind tunnel to get to a Reynolds number around 1 million. But we found that to get that Reynolds number, we need to operate the wind tunnel at around 100 feet per second. So the wind tunnel was brought up to that velocity, and the airfoil, we could rotate the airfoil and change the angle of attack. The first thing we did was try to find where the airfoil stalled. To do that, we moved the airfoil until we heard a kind of noise that that signified that the flow separated. And also we were looking at the manometer to make sure that to see where the flow separated, the pressures dropped all the way, not all the way, but significantly enough. And we found that separation occurred at alpha equals 17 degrees and alpha equals negative 16 degrees. And then after we found where separation occurred, we could use that data to find data for our specific airfoil, our specific angle of attack. Lab Group A6 was assigned to alpha of 14 degrees and alpha equals negative 7 degrees. So the way we did that is we tapped up the airfoil with 34 pressure taps. There were 17 on the top and 17 on the bottom, or 17 on the upper surface and 17 on the lower surface of the airfoil. And these pressure taps would be connected to the manometer here. As you can see, the manometer, there is 1 through 17 labeled here for the upper surface. There's 2 that are not labeled, and those were 2 for atmospheric pressure, static, and total pressure of the atmosphere. And then from there, 19 to 36 were labeled for the lower surface. And so these pressure taps would correspond to the pressure. And the pressure readings were in inches of alcohol. So we had to convert that, and that'll be discussed later on. And the way they were measured, we would turn the airfoil to the specified angle of attack. For us, it was 14 and negative 7. So at 14, we would turn the airfoil to 14 degrees. At that point, the flow would go over at 100 feet per second, and we would measure the pressure, and a group member would read it off, another group member would put it in Excel. That's how we measure the pressures at 14 degrees and negative 7. And to measure wake profiles, we use the hot wire. We put the hot wire a little bit behind the airfoil. We move the hot wire up and down. We started around 24 inches, and we moved all the way down to 0 inches in the wind tunnel vertically. And this hot wire just measures velocity. And similar to Lab 2, the hot wire anemometer was moved up and down. And it was used for angle of attack of 14 and negative 7. We did the same thing twice. And so here are the results. For wake profile at angle attack of 14 degrees, you can see it's a pretty big wake. There's a lot of velocity loss here. And this makes sense because at a high angle attack, you're going to have a lot of more losses to velocity. And the same idea is displayed here at an angle of attack of negative 7. As negative 7, as you can see, the wake is not as egregious as at 14 degrees. And this is because at negative 7, there's less cross-section for the flow to go over, or more cross-section, I'm sorry. And that is the results we got from the wake profile.
Hello, my name is Jason Miller, and today I'm going to be talking to you today about how we found our CP values, our CM values, and ultimately our CL values, and also the graphs that are associated with those calculations. So first, we're going to talk about the CP calculations. Now this was found by taking the difference in the static pressure and the local pressure at the various pressure tabs along the chord of the airfoil. Some important features of this calculation is that we multiply by the specific gravity because the manometer bank uses alcohol, along with the angle of the manometer bank because that can be adjusted in order to easily read what the different pressures are. Now all this is divided by the dynamic pressure, which we calculated as 1/2 rho v squared, where the density and velocity are both calculated in an Excel equation. Now it is important to note that there is a CP at each chord location for the pressure tabs at the upper and lower surface. Now our next step is to calculate Cn. Now Cn is also found for each location at the upper and lower surface, and that's found to be an average of two CP locations that are right next to each other multiplied by the difference of their chord ratio for those locations. And so ultimately we'll get multiple different Cn values for the upper and lower surface. Then these can be averaged, or these can be summed, and then the lower can be subtracted by the upper to get a Cn for the entire angle of attack. Now our group had to find a Cn for every angle of attack, so these various CP and Cn upper and lower values had to be found for all of them. Now finally, CL can be calculated knowing that CL is equal to Cn times cosine alpha, where alpha is the specific angle of attack that was measured and recorded through a digital display. Now looking at our CP versus chord ratio graph, we can see that our measured data roughly matches the NREL data. The blue dots are our upper surface and our red dots are our lower surface. So we can see the blue dots and the red dots converging on each other until they get pretty close here at around 1, which is the trailing edge. The size of this gap is the difference in pressure across the airfoil. And now the red ones are positive and the blue ones are negative, meaning that we have high pressure on the bottom of the airfoil and low pressure on the top. And this matches our physical understanding of lift too. So all this data seems to be accurate, precise, and makes physical sense. Next, we have this CP versus chord ratio for an angle of attack of -7 degrees. Now this graph is very similar and follows the same trend as our NREL data, as the upper surface and the lower surface converge on each other and kind of intersect into a in decline together, which again matches our data for -7 degrees. Finally, we're going to look at our CL versus alpha, and here we can also see that we match the NREL data. The max we found was around 1.4, and our minimum CL was around -0.75. Now this is slightly off some of the magnitudes that was calculated from the NREL, where some of those values are around 1.25 for a max and -0.6 for a minimum. So those values are slightly off, but we follow the same trend. And additionally, we can look at this CL versus alpha graph and match it up to our stall locations at the different angles of attack as our CL starts to decrease at roughly around 17 degrees and -16 degrees, which is where we experienced stall when we were listening for separated flow.
My name is Robert Batchelor, and I will be discussing our calculations for the coefficient of drag as well as the corresponding graphs. In order to solve for the coefficient of drag, we needed to solve this complex integral. In order to solve that, we used Simpson's rule. The function that we used for Simpson's rule is displayed on the top right. Once we applied Simpson's rule to the coefficient of drag equation, we came out with this equation, where the S's, S1, S2, and S3 are defined over there. Once we calculated our CD, we plotted it against alpha in what is commonly referred to as the drag bucket. On the left is our data, and on the right is data acquired from airfoil tools. It was acquired using the Xfoil software. As you can see, both graphs have a local minimum around 0 angle of attack. One discrepancy between the two of them that should be noted is the difference in the magnitude of CD. It is believed that this difference comes from the Xfoil software. Then we plotted CL versus CD. Again, you can see that on the left is our data, and on the right is the NREL data. Both of them have the same general shape, as well as a local minimum, again, around 0 CL. It should be noted that the range of CD is similar between both of them. However, the range of CL is higher for our data than it is for the NREL data. Then we plotted CL over CD versus alpha. Again, on the left is our data, and on the right is the Xfoil data from airfoil tools. The shape of the graph between both of them is very similar, with the local minimum close to -5 angle of attack, and local minimum and local maximum at -10 and +10. In this experiment, we calculated coefficient of pressure, coefficient of normal force, coefficient of lift, coefficient of drag, and weight profile. We used knowledge from previous labs in order to get all this, and we compared the data we got with NREL and other sources.